Hello, Miss Thinker here, your daily source for mind-blowing facts, forgotten history, and powerful motivation. Today, I will talk about neutron stars. Imagine a star so massive its own gravity crushes it into a city-sized sphere. A place where a single teaspoon of its material weighs as much as Mount Everest. This isn't science fiction. It's the reality of one of the most extreme and fascinating objects in the universe, the neutron star. Today, we're diving deep into the cosmic abyss to uncover the secrets of these incredible celestial bodies. Our story begins with the death of a massive star, one much larger than our own sun. After millions or billions of years of shining brightly, the star runs out of fuel. The nuclear fusion that supported it against its own immense gravity ceases. What happens next is a catastrophic collapse. The outer layers of the star are violently ejected in a spectacular explosion we call a supernova, briefly outshining entire galaxies. But while the outer layers are blasted into space, the star's core implodes under its own crushing weight. If the core is massive enough, it becomes a black hole. But if it falls within a specific range, about 1.5 to 3 times the mass of our sun, something else happens. The gravitational collapse is so intense that it forces protons and electrons to merge, creating a sea of neutrons. This is the birth of a neutron star. All that mass, once spread across millions of kilometers, is now squeezed into a sphere just 20 kilometers in diameter. Think about that, the mass of 1.5 suns compressed into an object the size of a city like Manhattan. The density is absolutely mind-boggling. A sugar cube-sized piece of a neutron star would have a mass of about 100 million tons. The gravity on its surface is about 200 billion times stronger than on Earth. If you could somehow stand on a neutron star, you would be instantly flattened into a subatomic smear on its surface. This extreme gravity also warps space-time around it, bending light in dramatic ways. But density isn't their only extreme characteristic. Neutron stars are also cosmic speed demons. Thanks to the conservation of angular momentum, the same principle that makes an ice skater spin faster when they pull their arms, and the slow rotation of the original star accelerates to incredible speeds during the collapse. Many neutron stars spin hundreds of times per second. The fastest one ever discovered, known as PSRJ 1748-2446 AD, rotates an astonishing 716 times every single second. Its equator is moving at nearly a quarter of the speed of light. This rapid rotation, combined with an immensely powerful magnetic field, turns some neutron stars into cosmic lighthouses. These are what we call pulsars. The magnetic field of a neutron star is trillions of times stronger than Earth's. This field funnels particles and radiates powerful beams of electromagnetic radiation from its magnetic poles. As the star spins, these beams sweep across the cosmos like a lighthouse beam. If one of these beams happens to sweep past Earth, our radio telescopes detect a regular pulse, a rhythmic beat from the heart of a dead star. It was this regularity that first led astronomers to discover pulsars in 1967. Initially wondering if they had found signals from an alien civilization. The interior of a neutron star is a realm of physics we are still struggling to understand. As the pressure builds, the atomic nuclei themselves are squeezed so tightly that they deform into strange, exotic shapes. Physicists have nicknamed these formations nuclear pasta. They theorize that there are layers of gnocchi, spaghetti, and lasagna as the matter transitions from a solid crust to the liquid core. This is the strongest material in the universe. We think it has a solid crust made of iron and other heavy elements, arranged in a crystal lattice. Beneath this crust is a sea of superfluid neutrons. Superfluidity is a bizarre quantum state where matter flows without any friction. Deeper still, at the very core, the pressure and density are so extreme that we're not entirely sure what exists. Some theories suggest a soup of quark-gluon plasma, where the neutrons themselves break down into their fundamental constituents, quarks and gluons. It has a state of matter that may have only existed in the first microseconds after the Big Bang. Neutron stars are, in a very real sense, natural laboratories for exploring the most extreme physics in the universe. But what happens when two of these cosmic titans meet? Some neutron stars are born in binary systems orbiting another star. If that companion is also a neutron star, they will slowly spiral towards each other over millions of years, radiating gravitational waves as they do. Their final moments are a spectacular cosmic dance of death. In the last few seconds, they merge in a cataclysmic event called a kilonova. This collision is one of the most energetic events in the universe, second only to the Big Bang itself. The merger releases an incredible burst of gamma rays and sends powerful ripples through the fabric of space-time gravitational waves that we can now detect here on Earth. The first direct observation of a neutron star merger in 2017 opened a new era of astronomy. For the first time, we saw an event with both traditional telescopes and gravitational wave detectors. This multi-messenger astronomy gave us stunning confirmation of a long-held theory. These mergers are the universe's primary factories for creating many of the heaviest elements. The gold in your jewelry, the platinum in industrial catalysts, the uranium that powers nuclear reactors, much of it was forged in the fiery collision of two neutron stars billions of years ago. The elements were then flung out into the cosmos, eventually seeding the clouds of gas and dust that would form new stars, new planets, and eventually us. We are, in a very real way, made of star stuff, and some of the most precious parts of that stuff come from these incredible cosmic collisions. There's another, even more exotic type of neutron star called a magnetar. These are neutron stars with magnetic fields 1,000 times stronger than a typical pulsar. They are the most powerful magnets known in the universe. This magnetic field is so intense it can visibly distort the shapes of atoms and even affect the vacuum of space itself. Occasionally, the magnetic field of a magnetar will undergo a violent rearrangement, causing a starquake. This unleashes an enormous blast of energy, mostly in the form of X-rays and gamma rays. A single magnetar flare can release more energy in 1/10 of a second than our sun will produce in 100,000 years. If a magnetar were to go off within a few dozen light years of Earth, it could potentially strip away our atmosphere. Thankfully, the nearest known magnetar is thousands of light years away. From spinning pulsars to cataclysmic mergers and impossibly magnetic magnetars, neutron stars push the laws of physics to their absolute limits. They are the remnants of stellar giants, the lighthouses of the cosmos, and the forges of the universe's heaviest elements. They challenge our understanding of matter, gravity, and the very fabric of reality. Each new discovery, whether it's a new pulsar, a gravitational wave signal, or a strange glitch in a magnetar spin, brings us one step closer to understanding these magnificent and mysterious objects. They remind us that the universe is a place of extremes, filled with wonders far beyond our everyday experience, just waiting to be explored. Scientists are even using the precise timing of pulsars to create a galactic positioning system. Future spacecraft could potentially navigate the vast distances of space by triangulating their position from these cosmic lighthouses, just like ships at sea. Thanks for joining us on this journey to the edge of physics. If you enjoyed this cosmic exploration, be sure to like this video, subscribe to our channel, and hit the notification bell so you don't miss our next adventure into the unknown. See you next time!